Yes, in the last class we have seen the functionality of AND gate, how it was verified on the FPGA and how it was implemented on the FPGA. The same procedure can be used for the rest of the logic gates and for the rest of the combination circuits also. But where we are going with the sequential circuits, there I need a clock. So through the clock, I have to generate a clock from the FPGA. So now before implement my sequential circuit on the FPGA, what I need to know is generated clock on the FPGA kit is it can be directly used for my sequential circuit. If I use it, so what happening? So that we have to understand here. This is my FPGA kit where like combination circuit implementation can be done directly, where I have a switches from which I take input, and the combination of inputs will be processed over here. Processed means that lookup table will be taking care of generating the output. That output will be diverted towards the LED, so that the input combinations are taken and the output will be driven over there across the LED. We are able to see the output. That is the same procedure for the combination circuits. Not only logic gates, for any kind of a combination circuit like off adder or full adder, multiplexer, demultiplexers, might be like number of inputs will be more, so that constant file will be more. So that if you have given a 2 input, the constant file will be having 2 constants. If I have 4 input, I need to add 2 more constants. So that is how we can implement any kind of digital circuit, any kind of combination circuit on the FPGA. So now let us see where in the case of generating a clock, what is the issue that I will be getting here. It is, so this is what my reference manual of the FPGA kit, Digital Nexus DDR4 kit, where I have to observe one thing. I will have to go with the oscillator. There I have to see one thing. Nexus GDR board includes a single 100 MHz crystal oscillator connected to the pin E3. Means across the E3 pin, the crystal which can generate the 100 MHz. So let me draw the schematic over here. This is what my FPGA kit. 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 So here we'll be having a switches. We'll be having a switches, and here we have LEDs. So which were considered as the inputs. That and all we know considered as the outputs. And there is a core, we have it here. And now at the pin E3, what it is happening is there we have a crystal oscillator which will be generating around 100 MHz frequency. So now what I do is, so in the same way we can implement the AND gate here. Now I will be implementing a sequential circuit also. So now I have a sequential circuit over here. Let us suppose a counter where I wanted to display 4 count values. So count of 0, count of 1, and count of 2, count of 3. So these 4 bits I have to verify. For that what I do is I will be connecting it first bit over here, next MSB bit over here, next MSB bit over here, next MSB bit over here. So this is how like 4 LEDs will be changed. It will be becoming on and off. Based on that I can see the count. So first 4 LEDs should be indicating the 0000. After that it has to give the indication 0001. Then it has to go to the next case 00010, like that. Finally the counter, when it is generating the count of the 111, So these four LEDs has to make it on and off, becoming on and off. Based on that, we have to observe this is the sequence where across the particular LEDs, so that the functionality of the counter is verified. So for that, what I do is I will be giving two inputs over here. One is reset for the counter. I will be giving a reset. Another one is like I will be giving a clock. Now clock decide at what speed my LED should be becoming on and off. So if like a clock is very high frequency, having very high frequency, so that values which is at 000 and it will be going to the 0001 is also high frequency. It will be moving from one value of the count to the next value. So like that, within no time all the values will be visible over there across the LEDs. So now we have to remember one thing. If the clock which you are trying to provide to the counter, which is generated from the let us suppose, which is generated from the E3, let us suppose E3, let us suppose. So the E3 which is having a crystal oscillator with a frequency of 100 megahertz, so that the counter is also taking 100 megahertz. So my count across the LEDs will be blinking at a very high speed, which is around 100 megahertz. Means 100 megahertz in the sense within 1 second, within 1 second, the particular LED is having a blinking with the frequency of 10 to the power of 100 into 10 to the power of 6. So this many cycles, this many times will be changed within 1 second. So human eye cannot recognize the changes for sure. It will be treated as every time LED is on. But even like the changes occurring over there across the LEDs, but we are unable to identify. So that is the basic problem that we will be having when we do the implementation on the FPGA for the sequential circuit. Usage of the clock is very difficult task. So now what I do is I will be doing some implementation over here. I will be making some circuit over here. What I do is, instead of giving a clock directly right from the E3, I will be giving my E3 to the particular circuit. What this circuit will do is it will be generating a clock which will be very low frequency, which will be having a low frequency. So that low frequency, what I do is I will be providing that as a clock. So now with this, what I can do is, so whatever the frequencies that we have at whatever the high frequency that I have it, I will be dividing that frequency such a that within 1 second, instead of this many times the changes we are unable to see. So what I do is I will be converting into within 1 second. I will be changing to 3 times. So what I do is whatever the frequency that I have it, this is what input frequency. This is called a system frequency, like system clock. We call it as a system clock. E3 is nothing but a system clock which will be operated at this frequency. So we call it as a system clock, F clock. So now um, what I do is system clock I will be converting into new clock. Right. So here this is what my system clock, this is what my new clock. So who is trying to do that one? This is the circuit which I'm trying to implement, extra circuit which I'm trying to implement, that will be taking care of that by taking high frequency over there as input and generating very low frequency. That low frequency signal, the low frequency clock is applied to our sequential circuit, so that our sequential circuit will be operated at very low frequency. It will be changing my LEDs, changing my outputs at very low speed. So at very low speed the LEDs also will be changing its state, so that we able to see the changes across the LED. Human eye can recognize it now. When within 1 second there are 3 times that particular LED will be changing. Means within one cycle there will be change of count values 0000 to 0001, and then it will be going to the 0010, means it will take around 1 second. Another 1 second it will be going to the count of 0011 0100 0101. So up to where it will go. So like that it will take 1 second to reach for the 3 count. So like that the count values can be visible over here, so that we can verify the functionality, right, by designing the circuit over here. We call it as a clock divider. So now I have to implement a circuit called clock divider. What it has to do, it has to take the frequency of this much and it has to generate a frequency of this one. Means that input frequency over here it should be 10 to the power of 8, 10 to the power of 8, and output frequency for this one should be it should be 3. So 10 to the power of 8 is the input frequency and 3 is the output frequency. So now what it can be, how it can be done, let us see how it can be done. For that what I do is the basic basic operation of a flip-flop is basic functionality of the flip-flop is, if I put one flip-flop JK flip-flop, if I give a clock frequency F, it is able to generate a frequency of clock by 2. So the input frequency will be divided by 2 times. If you see this is what your JK flip-flop, let us suppose this is what your clock. As you give that input j equal to 1, so that what happening, it will be toggled for every positive edge. This is my positive edge, this is another positive edge, this is another positive edge. So for every positive edge, this is how like output will be changed. So over here it output will be changed, again that output will be changed at this moment. So this is how input for the a flip-flop and this is the output for the flip-flop. So what happening is, input for the flip-flop if it is F, output for the flip-flop is F by 2. So using this basic concept, what I do is I will be using two flip-flops now, right? It is nothing but a 2-bit counter. So what this 2-bit counter will do is, the given frequency of F, it will be divided by 2 up to here, and again it will be divided by 2, so that F divided by 4 will be generated over here. So like that I will be keeping 3 bits over here, so 3 flip-flops over here, so that I can generate F by 8. So like that what I do is I will be making a n-bit counter. I will be designing a n-bit counter. When I give the frequency of the input is F, so there will be output over there. This is if it is a n-bit counter. If it is n-bit counter, the frequency over here is 2 power n. So this much frequency you can generate by the n-bit counter. So now our aim is to identify the value of n such that this n-bit counter is able to generate the frequency of 3. So now given the frequency over here, it is like 100 megahertz. It is nothing but 10 to the power of 8 hertz, right? So we need to generate around like output is 3 hertz. 3 hertz in the sense 3 times changes required for within 1 second. So now what I have equation is f divided by 2 power n, it should be 3 hertz, where my f is that this frequency need to be divided by this many times. F is 10 to the power of 8. So where I have to calculate n, my n. So here what I do is 2 power n is equal to 10 to the power 8 by 3. If I use logarithm at in the new in both sides, uh, log of 2 power n is equal to log of 10 to the power of 8 minus log of 3. Log a by b is nothing but log a minus log b. Yes. So if you solve this one, n log 2 is equal to 8 log 10 minus log 3. So from this n is equal to 8 log base 10, log 10 base 10 is a 1 minus log 3 by log 2. If I solve this one, this is around 8 minus 0.0.47, 0.30. So we got it the value around 25. So it says there should be a there should be a there should be a 25-bit counter I have to design. It's not required a 25-bit counter we have to design. What we do is I will be designing a 32-bit counter, and at a 25th bit I will be taking it as output, so that whatever the frequency I will give it, right, oh, the output is f divided by 2 power 25, so that this frequency will be 3 Hz. So this frequency will be around 10 to the power of 8 Hz. So now what I do is, whatever the system clock that I have at a very high frequency, which is generated across the quad oscillator, crystal oscillator, now using my system, using this kind of a digital circuit which I'm trying to implement over here, so that input, that circuit will take a system clock and will be generating a new clock with the frequency of 3 Hz. So now 3 Hz, if it is given to the input of your counter circuit, will be there will be output across the counter circuit will be like a count values which are changed for 3 times within the clock. So now let us create a Verilog source file for clock divider circuit. There are like input clock will be taken as it is for that circuit, which is called system clock. Yes, and it will take a reset also, and will generate a output as a new clock. Yes, so inputs are clock. Let me declare clock as input, and reset also input. So let me declare here itself output. What I do is I'll be generating a new clock as output, 31 down to 0. I'll be creating a temp register here. So let me write a procedure here using procedure statements. Always at the rate posedge clock. It will be taking a clock as input, positive edge of clock, and begin end if reset equal to 1. So temp register, like I will be making it into 31 bit, 32 bit 0. I will be making all the things are 0. temporary register is made it 0. I will be making reset. Else, so whatever the temp register that I have, I will be updating with the uh, temp plus 1. It's like incremented. It's nothing but a counter where it has to be counted for every positive edge when there is no reset. Otherwise, when it is a reset, it will be going to the 0 state. So now what I do is I will be using a SN statement over here, behavioral data flow statements. SN over here. So there is a counter. There is a counter. 32-bit counter. I have it, but I don't want to divide the input by 2 power 32. Yes, what I need, I just want to divide that input by 2 power 25. So what I need is I will be assigning my new clock which will be taken across temp register of 25th location. So where I can say one thing, if it is a 32-bit counter, so there is a first bit, it will be dividing by 2, second bit divided by 4, third bit divided by 8. So like that, n bit divided by 2 power n. So what I need is 25th bit I need, so that 25th bit I will be taking it as output. So 25th bit I will be taking it as output. So here 25th bit of the temp register I will be taking it as a new clock that will be taken as output. Yes. So for observation, if you wanted to see any location how the frequency is generated, assign newclktest is equal to, let us suppose I will be taking a clock from 20th location. So means 20th location in the sense 2 power 20. That frequency which may not be 3, so may be high, so that frequency you will be able to observe, able to recognize or not, we don't know. So let us see, at a 20th location the frequency is frequency by 20, so which will not be very small, so which may not be like identified. Let us see that the new frequency which is I'll be taking another frequency over here, new clock test. So new clock test that will be located at a 20th location. That will be located as a 20th location. So I will be taking two clocks. This is for test purpose. This is what I know, like 25th location for sure. It will be giving a 3 edges so that I can monitor the output on the LED. So I have to mention the output here also. I have to declare that. I forgot to declare this. So whatever the new output, I'm trying to take it as a output, so that I have to mention it here. Yes, this is what my program now. What I do along with the .p file, I have to add UCF file also. I'll be creating a new UCF file. So I'll be doing that later on. So let me do it, this one as a top level module, set as top level module, continue. And here user constraint file I can generate through IO planning ahead. Yes. So coming to my ports where I wanted to locate is, so new clock I wanted to see at C. This is what my FPGA right now. So right now I am not going to design a sequential circuit. Just I design one circuit which is required for my any kind of sequential circuit. So this circuit I am trying to implement, where input is taken from the E3 and reset is also taken as input. So the two inputs when I'm giving to this circuit need to generate two outputs. One is newclk, another one is newclktest, right? So what I do is, so here I will be trying to implement a module. I will be implementing a module which will be taking two inputs. One is from the E3 port, so this is called a clock, which will be at a 10 to the power of 8. This much frequency I have it, and I will be taking a reset also. What I do is reset from this port. I will be taking a reset from this port, so when I give these two inputs, so it has to generate two outputs. I will be locating these two outputs to two LEDs, right? So there will be two LEDs of this one, so which will be names as first two LEDs, which will be located at L16, sorry, K15 H17, K15 H17. So this is what displayed over there. Let me display a new clock from this one, and here let me display new clock test. So which will be changing the blinking, it will be done at 3 Hz. So with this speed it will be blinking, and we don't know at what rate it will be blinking. So you can monitor this one. You have to know whether you are able to monitor this one or not. You have to recognize the speed of blinking. For sure you can recognize the speed of blinking of this one, right? So let us test that. So first of all, let us do the pin mapping. As we know, the clock we have to generate from the system clock, which is generated from the oscillator. So we have to verify that there at E3 there is a clock generated from the crystal oscillator. So I have to give the location E3 here, and new clock where you wanted to locate. New clock you wanted to locate at K15, K15, and newclktest. Newclktest you wanted to locate at J17. J17. This is J17. This LED is J17. J17. And reset. The switch, first switch is your reset switch. This is J15. J15. So now let us export this IO ports. So I will be selecting UCF as it is. Give OK. I will be going for the second time also. Let me use this file. So this is the netlist, sorry, UCF file with different constants for each input. So let me close this one, and let me go with the UCF file which is created. UCF file, open it. So there is nothing. What you do, just copy it and save it. So this is how .v file and .ucf file you have it. Combinedly you have to go with the synthesis process, and you have to generate a programming file with this. So once the programming file is generated, we have to go with the dumping, and we have to observe that implementation is done for the clock divider circuit on the FPGA. Yes. So configure target device. Let us do the boundary scan. Right click, initialize chain. So my configuration file will be assigned, bit file will be in the D drive. D drive project location. So here bit file is generated for the clock divided circuit. Open it. I don't want to add any SPI. Okay, and let us do the program. So let me open my bit file. I don't want any SPI file, and let me do the program. Right click, program. Program is done. You can see the program is done. So program is done. So this is the program LED on, and where you can see this LED is blinking, and this LED is not is even it is blinking, we are unable to see that the speed at which it is blinking. So what I observed is, you can see within 1 second it is like able to blink it for 3 times. So the frequency of this one is 3 Hz.